Hello, so today we are talking about geometric random variables. Now, geometric random variables are similar to binomial random variables, but a little bit different, and we're going to talk about those differences today. So, if we compare binomial distributions and geometric distributions side by side, let's take a look at their differences and similarities. So if we think about BINS for binomial random variables, our little acronym, B, there are only two outcomes, success or failure. That's the same for geometric. So for geometric, success, failure, only two outcomes. I, observations are independent. That's the same for both of them. So in geometric distributions, the previous trial does not change the probability of the second. The N is where we see a difference. For binomial, we were given a set number of trials. For geometric, what we're looking for is how many trials does it take to get the first success. For example, how many times must I flip a coin before I get my first tails? Or how many times must I roll a die until I get my first 4? So this is the big difference for geometric distributions. We're looking at the probability it takes n trials until I get my first success. And the probability for each trial is the same, or the probability of success for each trial is the same. So we have a new formula for geometric distributions. Make sure you get this formula down because we're going to correct it a bit. But the first key point is a geometric random variable x. So we're still defining random variables as x. Looks at the number of trials until the first success. And this is where we see our big difference. So let's dissect the formula a bit. If we break down the first piece is the probability x equals n. Well, this n right here is saying the probability our first success is on the nth trial. So we're saying, what's the probability I don't get a success or I fail every time before trial n? So in order to find this probability, I need to first find what's the probability of a failure. Well, that's 1 minus the probability of a success. So if I think about not succeeding until the nth trial, that means I fail every time before my first success. So we do the probability I fail raised to n minus 1, or every time before my first success. And then the last piece of my formula is that P. This is when I finally have my success. There's only one success, so P does not have an exponent of a number greater than 1. This is really just saying there's one P, there's one success. Every time before that is a failure. So if we look at an example and apply this formula, it says, suppose that 20% of a herd of cows is infected with a particular disease. What is the probability that you would find your first infected cow on the 8th cow? Well, this is a kind of weird problem. We're talking about cows with diseases. If I want to know the probability that x equals 8, or that my first infected cow is the 8th cow, that means the first 7 cows are not infected, and then I find an infected cow on the 8th. So just to review, I found that 7 right here by doing 8 minus 1. So that's how I found that 7. Well, if I plug this into my calculator, I get 0.2097 times 0.2, and that gives me 0.0419 or 0.042. So if I have to interpret that, what this 0.042 is saying is the probability my first infected cow is the 8th cow is 4%. Or, kind of in more simple language, there is a 4.2% chance we find our first infected cow on the 8th trial. So, there's a 4.2% chance we find our first infected cow on the 8th trial. That would be a complete answer for A. B says, what is the probability that you would have to test 3 cows in order to find your first infected cow? Well, if I think about what this problem is asking me, it's saying I would have to test 3 cows in order to find the first infected cow. So what's the probability that x equals 3? Well, that means the first 2 are not infected, or raised to the 3 minus 1, but then I find my infected cow on the 3rd cow. Before you type this into your calculator, I want you to just think about, is this going to be a higher probability or a lower probability than part A? Just think about that for a minute. So, when you plug it into your calculator, you're going to get 0.64 times 0.2, and that gives me 0.128. So it's a bigger probability. There's now a 12.8% chance we find our first infected cow on the 3rd trial. So this is using my formula. Up here and right here we see 2 examples, and we see how to write our answers in context of the problem. But similar to binomial, do you think that there's a way our calculator can help us kind of minimize some of this arithmetic? Yes, you are correct. Your calculator does have a way of helping you do this. It's the same place as binomial, second vars or second distribution. Then there's 2 options, Geomet PDF and Geomet CDF. And like we said before, PDF is for my equal signs, CDF is for my less than or equal to sign. So, P is the probability, we enter that first, separated by a comma to then X. And X is the trial when you get your first success. So there's only 2 pieces we enter after Geomet PDF or Geomet CDF, but it's the same location as binomial. So if I'm using my calculator, though, I still have to write out what P and X are, what the probability I'm looking for is, and then interpret in context of the problem. So if we do these 2 examples again with the calculator steps, and like we would using the calculator, it says what is the probability you find your first infected cow on the 8th cow? You would need to write the probability x equals 8 equals, well, since it's equal signs, this is Geomet PDF. The probability of an infected cow is 0.20, comma, I want my first infected cow on the 8th cow. I also have to write probability of infected cow equals 0.2 and success on the 8th trial. So I have to include these 2 pieces if I'm using this notation. But if I use my calculator, you'll see we end up getting the same result. We get, oops, I need my pen. We get 0.0419 or 0.042. So there's a 4.2% chance that my first infected cow is on the 8th cow. Same thing down here. If I'm doing the example with 3 cows, the probability that x equals 3 would be geomet PDF, because it's equals 0.2, comma 3. And when I do that, I get 0.128, or 12.8%. Also, I would need to write this down here, but change it to the third trial. So I would have to include all of this information. I can't just write Geomet PDF. I have to include what I'm looking for, what the probability is, and when I want my success. So just like binomial and just like discrete, we can also find mean and standard deviation for geometric random variables. So the mean of a geometric random variable is mu equals 1 over p, or 1 over the probability. The standard deviation is the square root, of 1 minus p over p squared. And then this formula down here, this is kind of like the extra or bonus formula. The probability it takes more than n trials. So sometimes your problem's going to say, what's the probability it takes more than 10 trials, or more than 5 trials, or more than 50 trials to get my first success? It's not going to say your first success is the 50th. It's going to say more than 50 trials, and this is the formula we use for that. So let's take a look at an example. If we stick with the cows, it says, what is the expected number of cows that you would have to inspect until you find a cow that has a disease? Well, expected number, that's my mean, and we know the mean is 1 over p, or 1 over 0.2, and 1 over 0.2 is 5. So 5 cows. So I would expect that I would have to look at 5 cows before I found 1 cow with the disease. What is the standard deviation? Well, the standard deviation is the square root of 1 minus p over p squared. So the square root of 1 minus 0.2 over 0.2 squared. Do that piece by piece in your calculator and you will get the square root of 20, which is 4.472. So the standard deviation, or sigma, is 4.472, and I found it by plugging into this formula and being very careful in my calculator. So part E, or to finish this problem, it says, what is the probability that more than 7 cows would need to be tested until a diseased cow was found? Well, this more than 7 cows is that formula that we were just looking at, the bonus formula. The probability that x is greater than 7, or it takes more than 7 cows, just means that I fail, or I don't find an infected cow on my first 7. So the probability it takes more than 7 means that I fail my first 7. I'm going to make that look more like a 7. So failing is 1 minus the probability of a success raised to the 7th power. And when I do that in my calculator, you are going to see that the probability of more than 7 is 0.2097, or if you round that to 3, it'd be 0.21. So there's a 21% chance that it's going to take more than 7 cows to test until a diseased cow is found. So this is a really common problem, the more than problem, and this is more common in kind of real life examples. You don't want to know exactly this many. You just want to know what's the probability it takes me more than 5 people or more than 100 people. And this is the formula we use to find that. The probability I fail, or I don't succeed that many times. So that's our second key point. The probability it takes more than n trials means we fail n times, and this is that bonus formula that we saw. So that's a wrap. We can find the mean and standard deviation of geometric random variables. In geometric random variables, look at the number of trials until the first success. That's the big difference from binomial. So this is section 6.3 in your textbook. Look there for extra examples and practice problems, and make sure that you take a look at some of the calculator steps. See you later.